Good afternoon, everybody, from our behalf also. My name is Hannele. I'm a PhD student at Ghent University in Belgium.
And I'm Vincent Gagnon, and I'm a postdoc in transition. I was in France at École de Nantes, and I'm going to Canada with Kayla for next postdoc. So,
yeah, we would like to present an overview on the fate of metallic nanomaterials in constructed wetlands. It is indeed has a history. This presentation, about 2 years ago, we met in Ghent in Belgium, and we were assigned to do a co-presentation for Pula, which we did last year, and so this is a second version of that, hopefully improved. Our presentation is in 3 parts. So the first one deals with the source and form of nanomaterials possibly entering the constructed wetlands. The second part is about the question, what happens to the nanomaterials in the constructed wetlands when they end up in there? So what are the transformations that can occur? And the second point is, can they be toxic to the plants and microorganisms that are present in the constructed wetlands? And finally, we come to the point where we want to look at if there is a risk of the nanomaterials being released from the constructed wetlands. So, if we start with the first case, what is the source of the nanomaterials entering the constructed wetlands? We know that constructed wetlands are used to treat different kinds of wastewater, for instance, domestic and industrial wastewater, but also landfill leachate and stormwater. And out of literature, we know that nanomaterials have been found to be present in all these kinds of wastewater. So it's not really anymore the question of there is a possibility that they can enter. The question is more in what form can they enter and in what concentrations. We have also learned from the literature that there are, before the nanomaterials enter the treatment plants, there are transformations that can occur in the sewage pipes and the settling tank. So we are not expecting to have pristine nanomaterials in the constructed wetland because of these transformations. What comes to the concentration of the nanomaterials expected in the wastewater, these values are estimates based on production data, and they are, as you see, quite different from each other. And as I said, as when we consider the sewer system and the settler, which are before the constructed wetlands, we can expect that the concentrations of nanomaterials in the wetland influent are even lower than these values. So when we move on to the second part, we bump into a small problem that there is really no data on constructed wetlands and nanomaterials. Well, what we have done is try to filter out mechanisms which are reported for other related environmental systems, such as soil and activated sludge treatment, and look at these from the point of view of constructed wetlands, and if it would be possible that these mechanisms would then occur also in the wetlands. Here we have a little overview of those possible mechanisms. First of all, precipitation. Wastewater is really rich in different kinds of ions, and it's possible that these ions and the nanomaterials react together, forming precipitates. And a lot of these precipitates are more stable and more prone to stay in the wetland than as the actual nanomaterial. This is in case, for instance, for silver, which forms silver sulfide precipitates, even apparently in oxic waters at very low sulfide levels. And we know that sulfide is also present in constructed wetlands, so we expect that to be a major transformation that the nanomaterials can undergo in the constructed wetlands. Then aggregation, as the small single-size nanomaterials are not really prone to settle, but they are really easily aggregated because of the complex nature of the wastewater. It has a lot of other particles and colloids, etc., which can aggregate with nanomaterials and then cause settling and retention in the constructed wetlands. There are different parameters affecting the aggregation. Some of them increase the potential of aggregation, and some of them, like the dissolved organic matter, decrease the potential. But overall, it's probable that they aggregate in that kind of complex matrices. And what comes to absorption is that constructed wetlands, if we consider subsurface flow constructed wetlands, have a very high surface area. For instance, biofilm, plant roots, and present sludge and TSS have provide a large surface area where the nanomaterials can bind to. And therefore, it has even shown that when the TSS in the effluent is decreased, then you decrease also the concentration of escaping nanomaterials. And this was done for silver nanoparticles. Plants, some of them are hyper accumulators for metals. So the question is, would they also be able to accumulate nanomaterials in constructed wetlands? Well, research shows that the effect of the plants is quite low in comparison, for instance, to organic matter. But there are some differences between particle sizes, types of particle, and plant types. But as I said, overall, the concentration in the plant material itself is rather low. And also, the highest concentration is always found in the root zone. This is a table which gathers some research data on the plant uptake of different kinds of nanomaterials in wetland plants. You can see that there the mass of nanomaterial per gram plant material is rather high on the first rows, which are the hydroponic systems. But then when we add soil in the system, suddenly we have a much lower mass of nanomaterial per plant biomass. And this probably indicates that the soil is the more likely place for the nanoparticles to adsorb to. And now I'm going to give him the turn to Vincent.
Thank you. Okay. The other question, now we're inside the constructed wetland, and since a constructed wetland, it's an ecosystem, it's a living system, so there's some plant, there's some microorganism. The question is the nanoparticle, would it be toxic to the plant or the microorganism that will make the system non-functional? So if you want to treat something, but you're killing your system, it's not really good. So for plant toxicity, in the literature we found that you need a relatively high concentration of nanoparticle to really induce a toxicity to the plant. And this toxicity or this concentration is really dependent on the plant species and the type of nanoparticle. The particle size and surface area are a better indicator of the toxicity of this nanoparticle than just the concentration. And one reason why is that the pore size of plant wall are between 3 and 8 nanometer. And there's a lot of nanoparticles that have just greater size that won't enter the plant. However, it may that the nanoparticle just enter the plant by just pushing through the wall. So it can form a pore just by entering the cell. So that's also a possibility. So for the literature review on the toxicity of nanoparticle on plants, okay. You see, there's the red are when it's toxic or there's an effect, and the black is no effect. So half of what was surveyed had a toxic effect, and the other half had no toxic effect. And you can see the one that were toxic were the one that had like a smaller size compared to the higher size of the nano particle. And also there's some that were done in hydroponics, so only plant in water plus nanoparticle, compared to more complex system with soil. So the soil is a bit more representative for the toxicity than just putting a plant in a container and adding some nanoparticles. You will have a really different outcome. And the other thing is that the concentration that are used are really high to induce toxicity when you compare to what we saw at the beginning in what is estimated to be in the wastewater. So it's like an order of magnitude higher in those experiments that have shown that there was a toxicity. So the chance that wastewater will be, the nanoparticle in wastewater will be lethal or have a toxic effect on plant in concentrated wetland is quite low because the threshold is quite high. So the other part, one of the most important part in the concentrated wetland is the microorganisms that do all the transformation of pollutant, the carbon, the nitrogen. So how will it affect, the nanoparticle will affect this? The mechanism, it can damage the microorganism by creating reactive oxygen species. The dissolved ion can also affect the microorganism, or directly the nanoparticle can just stick on the membrane and have a lethal effect on the microbial population. However, it's a bit difficult to assess the toxic effect of those nanoparticles on microorganisms in a complex system like a constructed wetland, because there's no really standard tests how to do it. So different measurements give different results, and it's a bit hard to generalize. Furthermore, some tests were done and show that the microbial ecosystem in general can be quite resilient. And when you add nanoparticle, the ecosystem can shift a bit, but the function can stay the same, meaning that they will still do the treatment, but when you look at the microbial population, maybe they will shift to more resistant type of microorganism. Furthermore, the microorganism can produce some EPS, exopolysaccharide, in the biofilm to protect them against the nanoparticles, so they won't be as affected than if they were just on the surface. So, doing the literature review on the effect of those nanoparticles on the microorganism. So we have the different type of nanoparticle, the coating, the size, the toxic concentration, if there's some, the system. Those are an SBR treatment system. It's not a wetland, or mainly a petri dish size test. So on what I found, half of it have shown that there was no toxic effect at those concentration, and the other half have shown a certain kind of toxic effect. The first review on the SBR have shown a drop in performance for a couple of days, but it went up after. So there's an effect, but the microbial population can adapt, and they can become resilient on this toxic effect after a while. So there was an effect at the first pulse, but with time, this drop in treatment performance was not as drastic. In other circumstances, there were some effect, but the concentration were quite high. So we don't think that there will be a big effect on the microbial population in the concentrated wetland. So now let's pass to the last section. We're inside the wetland. Let's look at what happened outside if they can exit the wetland. So we know that the nanoparticle stick to the organic matter, so the TSS. So if the TSS come out, the nanoparticle will come out. So it's a bit proportional. And there was some experiment in treatment system and in the concentrated wetland, like my colleague here. So one of the first that will be published soon on nanoparticle and the exit of nanoparticle from concentrated wetland. So it mainly followed the TSS. If there's some preferential flow, that can have also an impact since the contact time in the wetland will be lower and can go from the inlet to the outlet. So that can be a way that the nanoparticle can come out. Furthermore, we found the case that the nanoparticle, if it's sulfidized, like the zinc nanoparticle, when it's sulfidized, it liberates ion at a greater extent. The dissolution of the nanoparticle is greater than compared for silver. So some nanoparticle, when they're transformed, they can have a different rate of dissolution of the nanoparticle. And finally, for the exit, another way it can exit the wetland, because there's three ways we've seen by the effluents or the water coming out. The second way that it can exit is through the sludge. Since in wastewater treatment plant, it has been shown that the majority of the nanoparticle were in the sludge, 90% or something in certain publication. So in concentrated wetland, if there's a settler before the concentrated wetland, we assume that most of the nanoparticle will be in the settler and not even reach the wetland. So, and the little amount that will reach the wetland, there's a good chance that it will be transformed and stay in the wetland. Except for the French system, the vertical flow French system, where they dump the old sewer on the vertical flow. There's no settling tank and anything like that, so there's sludge that can accumulate at the surface of the wetland. In that case, the nanoparticle risk to be in the sludge. Same thing for sludge drying bed. The particle will be in the sludge, and you see here a sludge drying bed with the sludge layer being taken out. And this, if there's nanoparticle in it, and you spread it on the agricultural field, there's some publication that say that a small amount of nanoparticle can be transferred to the soil, and that can be a way that it can exit the wetland in that case. It can also exit through the plant material, because plant bioaccumulate a certain amount, but as my colleague told you, they mainly accumulated in the roots. So if you cut the upper part of the plant and you compost this plant material, there's a low concentration directly in the leaf. So the exit through the plant, we think it will be quite low. So for the summary, before the wetland, the source is variable, the concentration and the type. We think that they will be transformed in the sewer system, and they will sulfidate, aggregate, and settle in the setting tank even before reaching the concentrated wetland. The nanoparticle that reach the concentrated wetland, there's a lot of different process in the wetland that exists to get rid of them, precipitation, aggregation, absorption, and plant uptake. And we think with the data that we have now that the toxicity level and the concentration that we saw at the beginning is quite low, and there's not a lot of chance that it will get toxic. And finally, at the outlet of the wetland, there's 3 ways it can go out by effluent, sludge, and plant. The sludge is the most probable because it's where it will be concentrated. And after that, by the effluent, if there's some TSS that come out of the wetland. But we think that it should, mainly be in the sludge layer. Finally, for some recommendation to future research, to have like concentration that are relevant to what we found in sewer, even though, as we saw this morning, sometimes the problem is that you get to detect it, but add some concentration that are relevant to the concentration that we found in sewer system. Don't use pristine nanoparticle, because if you're in a wetland, it travels through the sewer. So when it enters the constructed wetland, if you put like nice new particle coated and everything, it's a bit artificial because you don't have all the transformation that occur in the sewer. So it will be more representative to have some nanoparticle that were transformed before adding it to the constructed wetland. Standard do a toxicity test should be more standard, so we have a better idea of what is happening. And finally, the thing that is lacking right now is time, meaning having some analysis and see how does it accumulate in the wetland. And maybe they're not toxic, the nanoparticle right now because they're at low concentration, but if they accumulate on, 50 years, maybe after a while they will get toxic to the plant or the microorganism, or they will start to leach out of the wetland. So that's for sure future research that just follow those wetlands and see what happened after a certain amount of time to those nanoparticles that get in the wetland. So on that, thank you very much. And if you have questions, go for it.